All right, so we talked about pulse amplitude modulation, the mapper, the choice of signaling, the mapper, the choice of the pulse, and then, okay, we can choose a mapper, we can choose a pulse, we can choose the spacing between pulses. That's it. We also talked about the best receiver, or the receiver that I claim is the best. You haven't proven that, but the minimum distance receiver is what we would like to do. Okay. Now we will take a short detour into something which is actually prerequisites for the course, and that has to do with linear filtering. And the reason why we do this is to say something about the bandwidth of the transmitted signal, and later on we would like to relate that to constraints on this, the bit rate that we can achieve. Okay, so linear systems. What are those? There are systems which satisfy the superposition principle, right? So if I have a system, this box, I don't know if this is linear or not, but if I put in x1, I get out y1. If I put in x2, I get out y2. If I'm free to choose x1 and x2 to anything, or rather, if I take x1, multiply with a1, and I take x2, multiply with a2, and send that through a system, this system is linear if the output is the same linear combination of the corresponding outputs. So the superposition principle, right? So, and this property needs to hold for all choices of A1, A2, and all choices of X1 and X2. Okay. Time invariant systems means that if I delay the input, I get the same delay in the output. So if X is the input that produces the output Y, if we delay X with tau seconds, then the output is also delayed with tau seconds. So that's linear systems and time invariant systems. And if it's both linear and time invariant. And these are the things that we are mostly will work with. Okay. And why do I go through this? Well, we would like to say something about how pulse amplitude modulated signals, what happens when we filter them. Okay, that turns out to be important here. So, filtered pulse amplitude modulation. So, suppose we have a filter here with impulse response f of t. Okay. Now, I realize that this is very bad notation. F has nothing to do with frequency. It's just a function, right? But so this is an impulse response, and it's a function of time. So if we input the pulse that we use, g of t, if we input that into this linear time invariant system, okay, so this is linear and time invariant, then the output will be something, let's call it h of t. And we know from our classes in linear systems that the output is the convolution of the input with the impulse response. So this is g of t, the input, convolved with the impulse response, which was f. Like this. Okay, so now we know this. Okay, what happens then if I scale this pulse with some amplitude ak? What is the output then? In terms of h. So if I know that g produces h, what does ak times g of t produce? Very good. ak h of t. If I take ak and multiply that with gt delayed by k times capital T seconds, what is the output then?
It's the same, or well, ak g of time t minus kt.
Close. AK is right, but then it's h, right? Yeah. Okay. T minus kt, like this. Okay. So this is the linear property. This is the time invariant property. And let's do the linear property again and multiply and form the pulse amplitude modulated signal like this. And then we just get the sum of the corresponding outputs. So this is equal to S of t, and this is equal to the output when input is S of t. Okay. We recognize the form of this, right? It's also a pulse amplitude modulated signal. The only difference between the input and the output is that we have changed from G to H as our pulse shape. You see this, right? It's exactly the same. So, a very important come on. A very important conclusion is that if we have A, our symbols, and we do a pulse amplitude modulation signal out of that with pulse shape G, and T is the time between consecutive pulses, and we filter that with an impulse response F, then everything which is inside this box here can be replaced by another pulse amplitude modulator. And the only difference is that we have, instead of G, we have H. Right? Exactly the same thing. So this is nice when doing, simplification in block diagrams and so forth. We can simply absorb linear filters into the pulse shape of the pulse amplitude modulator. Okay, and of course H of t here is the convolution of G with the filter impulse response. Okay. And if I add more filters, I just add, I do this repeatedly and just convolve with the following filter, and so forth. I mean, I can keep on convolving here forever if I like. Okay, good. Any questions on this? So this was basically linear system theory, right? Okay, now, why is this important? Well, it's important because the first thing we do in the receiver is to filter the signal. Almost always, this is what we do. Explicitly with the filter, or it's just that our receiver electronics is a filter by itself, because no electronics have infinite bandwidth and so forth. Okay. So a very common receiver for PAM looks something like this. So here's the transmitted signal. So we have our AKs, which are formed from untransmitted bits. We have some signal, we have some noise, we have a receiver. And the first thing we do is to filter. And basically the objective with the filter is to suppress as much of the noise as possible. Okay, because noise is what's stopping us from making a good decision. Okay, so this is the bad guy here. So we want to filter this, and then we get another signal, let's call it Y. Okay, and what we do with Y is that we sample that, okay, and we sample that with the same rate as with what we transmit pulses. So it's the same T here, this T here is what we have here. Okay, same T. Okay, and then we get an output Y of K. In the best of worlds, we would like that Yk is equal to what? Ak, the input. That would be nice, right? That would be really nice, because then we have detected the symbols at the receiving end, and then we could just convert these symbols into corresponding bits, and everybody's happy. Okay, so that's the goal. So what is stopping us from this? Well, there are two things that could stop us. It's the noise, obviously, but there is something else. And let's first explore that something else. So let's ignore the noise for the time being, and then we add it a little bit later and see how it comes into play. Okay. So in the noiseless case, that is, let's ignore the noise, then the received signal equal to the transmitted signal, and then we better be able to decode the signal, right? Otherwise, I mean, what kind of design have we made if we're not able to transmit error-free over a noise-free channel? We will get fired, right? If I was working for Ericsson. Maybe I can still work at Chalmers, I don't know. But for sure, nobody would pay for that system, right? Okay, so YK, the output here, what is it? Well, it's the kth sample of Y here. And what is this? Well, it can be then converted into the desired thing, and that what we don't care about. Okay, so let's do that in a little bit more detail. So we know that y of t is this pulse amplitude modulated signal where we have our symbols, the ones that we are looking for, and then we have ht minus. Okay, so let's do this. Let's change summation variable. It doesn't change anything. Okay. Okay. So this is the output here. Okay. I can write that. The only thing I did is I changed from m to k in the summation here. It doesn't matter. Okay. And then y of k is y where I replace small t with k times t, which is then this sum, m from minus infinity to infinity, a of m, h, and instead of t, it's k times capital T minus m capital T, like this. Right? Just replace small t with k times capital T. And what's inside the argument here is k minus m times t, like this. Okay, so what do I want yk to be? Well, I want yk to be equal to ak. So let's pick out of this sum the term that I really care about, the one that corresponds to ak. That is when m is equal to k. So here we get a of k times h, k minus k t, like this. I just picked the m, which is corresponding to ak, therefore that would be when m is equal to k, so m is equal to k, so we get this, right? And this is, of course, h of 0. And then I get the rest, which I don't care about. So I get all the other terms, that is the sum from minus infinity to infinity, but not when m is equal to k, of am h t minus mt, like this. Is that okay, or is something strange? I just sampled the output signal and then pulled out the term which I care about and collected the rest in the second term. Okay, so this is desired, and this is undesired. Okay, and this is what we call the inter-symbol interference, or ISI for short. Okay, so now can I make this sum equal AK? What would be an ideal pulse shape? Well, I see that the samples, the t-spaced samples of this pulse shape is important. So if I take the nth sample here, what do I want that to be? Well, I would like this to be equal to AK. So I would like H0 to be 1. So it should be 1 when n is equal to 0. What should it be when n is not equal to 0? What would you like to have here? 0. And why?
Because then we don't get the...
Right, exactly. So if we make all the samples of h equal to 0, the whole term disappears. So this is what we aim for. We aim for a signal who goes through 0 every t seconds. That would be good, except at the origin where it should be equal to 1. Actually, it's not sacred that it could be 17 also. That would be fine, right? Or 32. As long as we know what the number is, we can always compensate for that when figuring out AK from YK. Okay. Such a pulse is called a Nyquist pulse. So, to illustrate the point here, let's pick an example where we have a pulse g of t, and say that for simplicity we center that around the origin, and we make the duration equal to t, where t is the time between consecutive pulses. And let's, for simplicity, pick f of t to be exactly equal to g of t. What is then h? Well, h of t is the convolution of g and f. So what would be the shape of that? Yes?
You get a triangle.
You get a triangle, exactly. So we get a triangle like this. At what time does it become 0? T, exactly. And here it will be negative t. Okay. As a matter of fact, if we want to find the starting point here, we take the starting point of the first pulse and the second pulse. Now it happens to be the same, but this holds in general. This plus this becomes that. This plus this becomes that. Okay. Is this a Nyquist pulse? It is, right? It's 0 at t, 0 at negative t, 0 at t. For sure it's 0 at 2t or negative 2t. Yeah. Has all the 0 points that we like, and it has something in the middle here, which is non-zero. Now, the amplitude here, that it's not necessarily 1, but we don't really care, right? So this is a Nyquist pulse. So we can get rid of intersymbol interference if the transmitted pulse is limited in time and the receiver filter is also limited in time, such that the extent of the pulse is at most 2t seconds. Right? Okay? And remember that the starting point is this plus this. the endpoint is this plus this. So then we can shift them, one can be wider than the other and so forth, as long as it fulfills that the overall duration from this plus this, which is the starting point, to this plus this, which is the end point, is 2t seconds, we're fine. Okay, so now case closed. We know how to do Nyquist pulses. What is the problem with this pulse? Actually, somebody approached me in the break and asked about this. A lot of bandwidth is required. And a lot of bandwidth is required due to these sharp edges here. So for sure we can smoothen that a little bit and we get something which is more compact in frequency. But suppose we want this to be band limited, completely band limited. So something that in frequency has a finite bandwidth.
A sync pulse.
A sync pulse, right? So we can replace this with a sync pulse. What is the problem with the sync pulse?
It's not limited in time.
Exactly, right. So pick your poison is the answer here, right? But now let's do some theory and say, okay, would this also work with sync pulses? And it's not obvious at all, but yes, it does. We can actually find Nyquist pulses if we replace this with a sync pulse and this with a sync pulse. And that is a little bit of magic, but it actually works. All right. So let's go along this path and see what we can find out. First of all, bandwidth. Here's the sorry state of things. Bandwidth is not there are definitions of bandwidth, but there are many out there, right? So when we talk about bandwidth in general, if we want to be precise, we need to specify which bandwidth we are talking about. So signal bandwidth should not be confused with the data rate, which is sometimes called the bandwidth when we talk about data communications. Okay? But we who are electrical engineers knows the difference between bandwidth and bandwidth, right? So data rate is bits per second and bandwidth is measured in hertz. The computer science people get this confused. So, okay. Anyways, suppose that GOT has a spectrum, a Fourier transform, which is this. Okay. Then the absolute bandwidth of this pulse, or of GOT, is defined as the difference between the highest and lowest, and here I would like to stress positive frequency. Okay. So that's the definition we will use in this case. This means that for baseband signals, which are centered around 0, bandwidth is counted from 0 up to the highest frequency. Okay. So we don't count negative frequencies here. And for passband signals, we have bandwidth which starts here. So this is the smallest positive frequency, and this is the highest positive frequency. So this is how we define bandwidth in this course. And I would actually recommend to adopt this bandwidth notion in other things also, because then things becomes nice and consistent. Okay. Right. So we continue. Now we know what bandwidth is. Now, suppose we have this full system again. We have our bits, we have a mapper, we have our symbols. We go through a PAM block here and we get the transmitted signal. We have some noise, received signal. We have our filter, we get Y, we sample that, we get output Y. So the same as before. Now we make the restriction that G has a certain bandwidth. And as we said earlier, if it has a certain absolute bandwidth, it can never be time limited. Okay? So it will have infinite extent. And the question is, can we still get a Nyquist pulse in this case, right? Which is not obvious. Okay. It turns out that if we restrict G to have a certain bandwidth W, okay, maybe this constraint is due to, we just want to conserve bandwidth on the channel. So W is given to us. Then it turns out that if the symbol rate is greater than twice the bandwidth, we're screwed. Okay. There is nothing we can do. We will have intersymbol interference. So it's not possible to do inter-symbol interference-free transmission. Okay, so that's bad because we would like to have a high RS, right? We would like to have a high data rate, and we can get a high data rate by increasing RS. Right? For a given mapper, if we increase RS, we increase RB also. However, if the symbol rate is equal to exactly twice the bandwidth, then it's possible to do inter-symbol interference-free. But it's if and only if the convolution between G and F is the sync pulse. Okay. We'll explore this further, right? But so the convolution of these two things needs to be a sync pulse. Sync is kind of a weird signal because the convolution of a sync with itself is the same sync. Yeah, so two syncs, this convolve with itself, it's itself. You can think about that during the weekend if you like, or maybe not. Okay, now if the symbol rate is less than twice the bandwidth, then we have many choices for this convolution, G of H. Remember that G times G convolved with H is the one that needs to be a Nyquist pulse. We're not concerned about this being a Nyquist pulse or this being a Nyquist pulse. We're concerned about the convolution of it to be a Nyquist pulse. Okay. So, but it says here that we can choose this to be a sync, and then we can do inter-symbol interference-free transmission. It also says that if the symbol rate is less than twice the bandwidth, there are many choices of this that will lead to inter-symbol interference-free transmission. Okay. So that's the highlight. Okay, well, and then this last bullet here is actually what we explored, that if we have something here which has a duration which is less or equal to t, and this also a less or equal to t, then we get a Nyquist pulse. Okay, so that's also possible. But as we already said 100 times, this will not lead to a band-limited transmitted signal. Okay. So let's go into this red box and see why this is true. Okay, so this is also kind of nasty, but let's do it. Right. So suppose we have a bandwidth on 1 megahertz. What is the maximum symbol rate we can do without introducing inter-symbol interference? I'll give you 5 seconds. 4, 3, 2, 1. So is it 1 megabit, 2 megabits per second, 2 megasymbols per second, or none of the above? This is evil alternative, right? So which one is it? How many for A, B, C, D? Right. Actually, this is the correct one. Okay, this is Swedish for correct. Okay, so you can have a symbol rate which is twice the bandwidth. Okay, it's not 2 megabits per second, right? Because we are talking about the symbol rate here. What is the maximum data rate we can have? Is it 1 megabit? 2 megabits, 2 megasymbols per second, or none of the above? How many for A, B, C, D? Great, very good, right? This is the correct. Because the bit rate depends on how many bits we have per symbol, right? So essentially we could choose that to be anything here. So bandwidth has a restriction on symbol rate. Bit rate is the symbol rate times the number of bits we have per symbol, right? And it turns out then that the transmit power would limit how many bits we can have per symbol. Okay. So bandwidth and power would decide this. Okay. We will see that later on. But right now we're talking about bandwidth, and we would like to maximize the symbol rate. That's our narrow scope today. Okay, so Nyquist pulses, we already talked about this. Here's a picture of Nyquist. He's actually born in Värmland, so he's a Swedish dude, but he did all his work in the US. Okay, so a signal, H, which is the convolution of G and F, is a Nyquist pulse if it's like this. We already said that. Now, the sampling theorem tells us that if we have a constraint on the samples, here we have the samples, we have a signal which is 1 when k is equal to 0 and 0 for all other k's. If we take the Fourier transform of this, we get 1. Okay? But the sampling theorem tells us also that yeah, let's go through this. But anyways, it turns out that this is the final answer. I will go through the derivations in a second. Okay, so this equality follows from the sampling theorem. And H here, this function, is the Fourier transform of the time continuous pulse, H. And remember, H is the convolution of the transmit pulse and the receiver filter. Okay. So there is an equivalent statement between, about something being a Nyquist pulse. There is a time domain condition, and there is a frequency domain condition. And which one we choose depends on which one is the easiest for us to process. Let me perhaps skip the derivation of this and then just talk about the implication of it. Okay, and then return to the derivation if we have a minute left. Okay, so the connection now we would like to do is between intersymbol interference, bandwidth, and symbol rate. Okay, essentially what I would like to do is to prove what's in the red box here. Okay, so I claim that we can do that by using this formula here, which I haven't proven. So if you believe that this formula is true, we can prove it. Okay, so now we make a few observations. If our pulse shape that we use for transmission is band limited, what can we say about H? Well, it's the convolution between G, which is band limited, with some filter F. Okay, but it's band limited at the beginning of the filter, so for sure it would be band limited at the outside of the filter, right? So H is the convolution between G and F, but then the Fourier transform of H is just the product of the Fourier transform of G and F. We know this, right? Now it's a little bit stupid because this F here, of course, has nothing to do with that F, but this you understood, I hope. So H of F would be 0 whenever the frequency is above W, right? Okay. So the key question is that if we have the Fourier transform and we form this thing, which by the way looks very much like a pulse amplitude modulated signal, right? We take a pulse and we repeat that, we delay it now in frequency at regular intervals of Rs, and we add that together. Okay. So the question is this equal to 1 over Rs? Because if it is, then we have a Nyquist pulse. Okay, so we would like all these H, if we add them together, to form a straight line like this. Okay, now suppose H looks like this. And suppose then that we have a symbol rate that looks like this. Then we see that we have a gap here. Now, if this gap exists, there is no way we can add these pulses together and get a constant signal, right? We would like to add these together, these pulses, to get it to be a straight line. And for sure, we cannot do that if there is a gap between the pulses. Because then, whatever the shape of the pulses are, we would have 0 in between. You know, regardless of what the pulses look like. You see this? Okay. So what we would like to do is to add the pulses together and get a constant. That is a constant straight line like this. But if the pulses are not touching each other, there will be gaps in between, and therefore the sum signal would be 0 there. So if the gap exists, there is no way we will fulfill this criterion, and we will have intersymbol interference. Okay, so what is the gap then? Well, the gap is Rs minus 2W. So the gap is greater than 0, which is the same thing to say, as Rs minus 2W is greater than 0. That is Rs greater than 2W. Okay. If that is the case, then H of t cannot be Nyquist. Okay. So basically we have proven the first statement here. Okay. Now if the gap is equal to 1, there is one pulse shape and one pulse shape only that makes it possible to get a straight line. Okay, so the gap is exactly 0. So these boxes are exactly touching each other. What would be the shape of the boxes in order to get a straight line? I want to get a straight line here by adding these things together. And we just barely managed to close the gap here. Exactly. So it would be very nice if they looked something like this. Right? Now, okay, maybe I should change color here. So it would be nice if they looked something like this. And if it looks like this in frequency, it's a box in frequency, what is it in time? Sync. And it turns out to be this sync. Okay, it's not a sync now, it's a box, right? But if you inverse Fourier transform this, you get a sync. Okay? And this proves this statement. Okay. And then finally, if the gap is less than 0, so the pulses are overlapping, then there are many choices of pulses in order to get a constant signal. Right? Okay. Right. So it could, for instance, be that something. Okay. Let's see if I can try to draw something. Suppose it's something that overlaps. If the overlap is something like this would work. Something which is constant and then is a triangle. And there are many things we could do in the overlap here in order for these to add together to become a constant. Okay, so in practice, what do? In practice, we use this. We would like to be in this domain. And the reason for this is that even though the sinks are nice in the sense that they are the ideal pulse, in theory, they're horrible in practice. Okay. And the reason for this is that they are very long duration, and the side lobes of the sink, if you remember how a sink looks like, it's something that goes like this. And the drop off here is very slow. Okay, and the problem with this, there are many problems with this, is that when you want to use this in practice, we need to truncate that. And we want to truncate when the amplitude is small enough. So we need a longer truncation limit. And that is not so nice. But there are also other theoretical problems with this. So one typically avoids sinks. One could try it, but typically one tries to avoid it. So instead we want to use pulses which are in this domain. And what is used in practice are these raised cosine pulses, or that's a family of pulses that are used. This looks horrible, these formulas here, so it's easier to draw what they are. They look something like this. So here is the spectrum, the Fourier transform of a raised cosine pulse. So HRC, RC for raised cosine. So why is it called a raised cosine? It's because it's a flat region, and then it's a half period of a cosine. So a cosine which is centered around here. So if I continue to draw this, it will be like a cosine like this. So that's why it's called a raised cosine. It's a flat thing and then a raised half period of a cosine. Okay. Important things here is that we have a flat region and then we have transition region. And the transition region is half a period of cosine. There's a transition width here, and the width of this is controlled by a parameter alpha. This alpha is known as the roll-off factor. The greater alpha is, the longer the transition period is, and the smoother the pulse is. Okay, and the smoother the pulse is, the more quicker it falls off. It's more compact in time. And this is typically something that we would like to have. Okay, the bandwidth of the transmit of this is given by the highest frequency component here, which is 1 plus alpha over 2t. So here's what the problem with increasing alpha is, that we increase the bandwidth also, which is something that we don't desire. T here is our regular thing. So T 1 over T is equal to Rs. Okay, in this, all right. So we would like that to be high in comparison to the bandwidth, which means that we also would like alpha to be small. Okay, so the bandwidth W is 1 plus alpha over 2T, which can be written as 1 over 2T plus alpha over 2T. And we know that intersymbol interference-free transmission is possible if Rs is less or equal to 2W. And we would like to get as close as that as possible. Another way to say that is W has to be greater than Rs over 2 or 1 over 2 Ts. Okay. So bandwidth here is 1 over 2 Ts, which is the smallest possible it can be, plus this penalty, extra bandwidth, that's the price we pay for this by using these pulses. And this is known as the excess bandwidth. Okay. And then finally, if we look at this in the time domain, these are the raised cosine pulses for different alphas. Alpha 0, then it's a sync actually, so this is not what we want to use. Alpha 1/4, it looks something like that, half and 1. And we see that it goes down quicker to 0 the higher alpha is. So in time domain, better and better behavior as we increase alpha, but worse and worse behavior in the frequency domain. We get higher and higher bandwidth if we keep 1 over 2T fixed. Okay, so that was very, very quick. But I think we have learned a lot today, I hope. We have talked about modulation, we have talked about pulse amplitude modulation, and we have talked about intersymbol interference and how to avoid intersymbol interference and how that is connected to the symbol rate and the bandwidth of the transmitted signal. So when we meet next time, which is next Thursday actually, we will talk about more how noise and transmit power comes into the equation here when we're trying to maximize the bit rate. All right, so have a nice weekend, and I'll see you in less than a week, but Thursday next week.